On January 20, 2025, China's experimental advanced superconducting Tokamak East, often referred to as the artificial sun, achieved a historic milestone in nuclear fusion research by maintaining a high confinement plasma for a record-breaking 1066 seconds. This remarkable accomplishment, announced by the Institute of Plasma Physics under the Chinese Academy of Sciences, signifies a significant advancement in the quest for clean and sustainable energy sources. Background of the EAST project. EAST, which was launched in 2006, is the world's first fully superconducting tokamak. It employs innovative design features such as a non-circular cross-section and fully superconducting magnets, enabling advanced steady-state plasma operation. These characteristics have established EAST as a unique experimental platform that fosters international collaboration in fusion energy research. Over the years, EAST has made significant strides in achieving and maintaining high-temperature plasma, which is essential for the fusion process. The recent achievement of sustaining plasma for over 1000 seconds more than doubles its previous record of 403 seconds set in 2023, highlighting the rapid progress being made in this field. Importance of fusion energy. Nuclear fusion, the process that powers the sun, has the potential to deliver a nearly limitless source of energy without the greenhouse gas emissions associated with fossil fuels. The primary fuels for fusion, hydrogen isotopes such as deuterium and tritium, are abundant, suggesting that fusion could provide a sustainable energy future. The fusion process produces only helium as a byproduct, making it an environmentally friendly alternative to conventional energy sources. Achieving stable and prolonged plasma operation is crucial for the development of future fusion reactors that aim to generate continuous electricity. The recent breakthrough at EAST is a significant step toward making fusion energy practical. However, experts caution that while this achievement is promising, it does not offer an immediate solution to global energy demands. According to Song Yuntao, director of the Institute of Plasma Physics, fusion devices must achieve stable operation at high efficiency for thousands of seconds to enable self-sustaining plasma circulation, which is critical for the continuous power generation of future fusion plants. Timeline of achievements. 2006 – Launch of EAST as an experimental fusion reactor. 2016 – Breakthrough in producing high-temperature plasma. 2022 – EAST sets a record with continuous plasma operation for 102 seconds. 2023 – EAST breaks its own record with a 403-second plasma operation. January 20, 2025 – EAST achieves a remarkable 1066 seconds of plasma operation. Technological advancements. The EAST reactor utilizes magnetic confinement to achieve and maintain high-temperature plasma. During the recent experiments, researchers made several improvements to the reactor, including doubling the output of its heating system. These upgrades are vital for sustaining the extreme conditions required for fusion reactions, where temperatures must exceed 100 million degrees Celsius to facilitate the fusion of atomic nuclei. EAST's design and operational advancements not only contribute to its own achievements but also provide valuable data for other fusion projects worldwide, most notably the International Thermonuclear Experimental Reactor ITER being constructed in France. China plays a significant role in the ITER project, contributing approximately 9% of the construction and operational efforts. Global collaboration and future implications. The success of EAST is not just a milestone for China, it also represents a crucial step forward in the global pursuit of fusion energy. The data and insights generated by EAST will support the development of future reactors, including China's upcoming fusion engineering test reactor ITER. Collaboration among international scientific communities is essential to address the challenges of fusion energy and accelerate its practical application. Although the dream of harnessing nuclear fusion as a viable energy source is still years away, the achievements made by EAST reaffirm the importance of continued investment in research in this field. The transition to clean energy solutions is imperative to meet the growing energy demands of humanity and combat climate change. Conclusion. In summary, East's groundbreaking achievement of 1,066 seconds of continuous nuclear fusion ignition is a significant milestone in the journey toward sustainable and clean energy solutions. While there are still challenges to overcome before fusion energy can become a practical reality, the advancements made by China's artificial sun contribute to the broader efforts of the global scientific community in the quest for fusion power. Continued innovation, international collaboration, and a commitment to research will be essential as we move closer to unlocking the potential of fusion energy for the benefit of all. The achievement of the experimental advanced superconducting Tokamak East, known as China's artificial sun, in maintaining a high-confinement plasma for 1,066 seconds marks a major milestone in nuclear fusion research. This accomplishment, reported on January 20, 2025, is significant not only for its technical achievements but also because it challenges some conventional perceptions about the progress of nuclear fusion technology. Counterintuitive information. 1. Perception of progress. Many people may believe that achieving sustainable nuclear fusion is just around the corner due to recent advancements like East's record. However, experts emphasize that while significant, this achievement does not equate to imminent commercial viability. Even with the new record, fusion energy remains a distant goal, suggesting a slower progression than public optimism might suggest. 2. Comparison to the sun. The notion that these reactors mimic the sun can lead to the misunderstanding that achieving fusion is straightforward. In reality, the conditions necessary for fusion on Earth are much more complex and challenging than those in the sun. The sun's natural pressure provides a conducive environment for fusion, while tokamaks like East must generate extreme temperatures over 100 million degrees Celsius and maintain plasma stability in entirely artificial conditions. 3. Record achievement and practicality. While maintaining a plasma state for over 1,000 seconds is a remarkable technical achievement, it does not mean that fusion reactors can produce more energy than they consume. Currently, all fusion reactors, including East, still require more energy input than they yield, which complicates the narrative that we are on the verge of a clean energy revolution. For the role of international collaboration, the narrative surrounding East often emphasizes China's advancements in fusion technology. However, the success of East is deeply intertwined with international collaboration, particularly its contributions to the International Thermonuclear Experimental Reactor ITER project. This highlights a collective global effort rather than a unilateral national achievement, countering the perception that fusion advancements are primarily a Chinese endeavor. 5. Abundance of resources. Although fusion fuel hydrogen isotopes like deuterium and tritium is described as abundant and a potential source for a near limitless energy future, the reality is that the infrastructure and technology to harness these resources efficiently and sustainably are still in development. This contrasts with the immediate availability of fossil fuels, which can lead to misconceptions about the readiness of fusion energy to replace current energy sources. 6. Environmental comparisons. While fusion is often touted as a clean energy source with minimal waste, the environmental impacts of building and maintaining fusion reactors, along with the mining of materials needed for reactor construction, can be significant. This may not be immediately apparent in discussions that idealize fusion as a perfect solution to energy and environmental crises. 7. Technological innovation. The advancements in East's technology, such as its fully superconducting magnets and innovative reactor design, are frequently celebrated. However, the practical application of these innovations in commercial reactors remains uncertain. Thus, while East represents a leap in understanding and technology, translating these achievements into functioning power plants is a considerable hurdle that is often underrepresented in optimistic narratives. In summary, while the achievement of 1,066 seconds of continuous nuclear fusion ignition by China's East is a landmark event, it is essential to recognize the broader context and ongoing challenges in the field of nuclear fusion. The complexities of achieving practical fusion energy, the collaborative nature of progress, and the environmental considerations are critical factors that temper the excitement surrounding these advancements. The report on China's experimental advanced superconducting Tokamak East achieving a remarkable 1,066 seconds of continuous nuclear fusion ignition is significant for several reasons, particularly regarding aspects that may easily be overlooked in the broader narrative of fusion energy development. 1. Technical innovations of East. While many reports highlight the duration of plasma operation, they often gloss over the specific technological advancements that make East unique. East is the world's first fully superconducting tokamak, which means it utilizes superconducting magnets that can operate at very low temperatures, drastically reducing energy losses associated with heating. Additionally, its non-circular cross-section allows it to maintain plasma stability more effectively than conventional tokamaks. These technical innovations are critical for future designs of fusion reactors and demonstrate how engineering breakthroughs can directly impact the feasibility of sustained nuclear fusion. Significance: understanding the unique aspects of East's design provides insight into how future reactors might operate and suggests that other countries aiming to develop fusion technology can learn from China's advancements. This could influence global fusion research and development strategies. 2. Contribution to international collaboration. The report mentions East's role in the International Thermonuclear Experimental Reactor ITER project in France. But it may understate the importance of international collaboration in fusion research. East serves as a testing ground for technologies and methodologies that can be implemented in ITER and other fusion projects around the world. The data and findings from East will not only benefit China's future fusion endeavors but also contribute to a global knowledge pool that could expedite the practical application of fusion power. Significance: the collaborative nature of fusion research is essential for overcoming the technical challenges that have plagued the field for decades. Enhanced cooperation may lead to faster advancements in fusion technology, which is crucial for addressing global energy demands. 3. Economic and environmental implications. While the potential for fusion energy to provide a near-limitless clean energy source is widely recognized, the economic implications of such technology are often overlooked. The transition to fusion energy could radically reshape global energy markets, reduce dependence on fossil fuels, and mitigate the economic risks associated with climate change. Furthermore, the byproducts of fusion, primarily helium, are significantly less harmful than the waste generated by fission reactors and fossil fuel combustion. Significance: acknowledging the economic and environmental benefits of fusion energy reinforces the urgency of continued investment in this technology. It positions fusion not just as a scientific goal but as a viable solution for energy security and climate change mitigation. 4. Long-term vision versus immediate solutions. Many reports present East's achievement as a significant leap toward practical fusion energy, however, they often fail to convey the complexity and time required to develop commercial fusion reactors. Experts including Song Yuntao emphasize that while this milestone is noteworthy, sustained operation at high efficiency for extended periods is essential before fusion can become a reliable energy source. This distinction is crucial as it shapes public and investor expectations about fusion energy timelines. Significance: by managing expectations regarding the timeline for viable fusion energy, stakeholders can better allocate resources and plan for gradual advancements rather than expecting immediate results. This realistic perspective is vital for maintaining public and political support. 5. The role of public perception and misconceptions. The general public often holds misconceptions about nuclear fusion, believing it to be a near-term solution to energy crises due to its portrayal as an artificial sun. While the technological advancements are promising, the challenges are still substantial. The complexities inherent in achieving and maintaining the conditions necessary for fusion, as well as the significant time frames involved in developing practical applications, are often underrepresented in media narratives. Significance: addressing misconceptions is crucial for fostering informed discussions about energy policy and research funding. A well-informed public can better support the necessary investments and initiatives that will lead to the eventual realization of fusion energy. 6. The broader context of energy transition. In the context of global energy transitions, East's achievement is part of a larger movement toward sustainable energy solutions. While the focus is often on renewable sources like solar and wind, fusion represents a complementary pathway that can provide continuous power, addressing the intermittency issues associated with renewables. This multifaceted approach to energy generation is essential for creating a resilient energy infrastructure. Significance. Recognizing fusion as part of a diverse energy strategy highlights its potential role in a balanced energy portfolio, ultimately leading to a more stable and sustainable energy future. Conclusion. China's East achieving 1.066 seconds of continuous nuclear fusion ignition is not just a technical milestone, it embodies a complex interplay of innovation, international collaboration, economic potential, and the need for realistic expectations. As the world grapples with energy challenges, understanding these nuanced aspects will be vital for advancing fusion research and integrating it into a comprehensive strategy for sustainable energy solutions. 1. Significant milestone in nuclear fusion research. China's experimental advanced superconducting Tokamak East achieved a remarkable 1,066 seconds of continuous high-confinement plasma operation, surpassing its previous record of 403 seconds set in 2023. This advancement demonstrates significant progress in sustaining high-temperature plasma, which is essential for the development of nuclear fusion reactors capable of generating continuous and clean energy. This milestone highlights the ongoing pursuit of nuclear fusion as a viable alternative to fossil fuels, emphasizing its potential for addressing global energy challenges. 2. Unique technological features of East. East is the world's first fully superconducting tokamak equipped with innovative design elements such as a non-circular cross-section and fully superconducting magnets. These features enable advanced steady-state plasma operation modes, allowing for greater flexibility in experimental configurations. This technological distinctiveness positions East as a key player in international fusion research collaborations and contributes to the broader understanding of plasma behavior in fusion reactors. 3. Implications for sustainable energy. The successful operation of East not only signifies a step forward in fusion technology but also has profound implications for sustainable energy. Fusion energy, which produces no greenhouse gas emissions and generates only helium as a byproduct, offers a near limitless and clean power source. The availability of abundant hydrogen isotopes as fuel suggests a sustainable energy future, making nuclear fusion a critical component in global efforts to transition towards cleaner energy solutions. 4. Challenges and future prospects. Despite the progress represented by East's achievements, experts caution that practical implementation of fusion energy remains a formidable challenge. Achieving stable operation at high efficiency for extended periods is crucial for future fusion plants to generate continuous electricity. While East's innovations and data will contribute to projects like the International Thermonuclear Experimental Reactor ITER, the timeline for realizing practical fusion energy remains uncertain. Continuous international collaboration and technological advancements will be essential to overcoming these challenges and making fusion power a practical reality for future generations. 1. The Manhattan Project 1942–1946. This was a secret U.S. government research project during World War II that aimed to develop the first nuclear weapons. Conducted in response to fears that Nazi Germany would create an atomic bomb. The project brought together some of the greatest scientific minds of the time, including J. Robert Oppenheimer and Enrico Fermi. The culmination of this project was the development of the atomic bomb, which was successfully tested in July 1945 and later used in Hiroshima and Nagasaki, leading to the end of World War II. The Manhattan Project marked a significant milestone in nuclear physics and technology, showcasing the potential of harnessing nuclear reactions, albeit for destructive purposes. 2. The ITER Project 2006 present. The International Thermonuclear Experimental Reactor ITER is an international nuclear fusion research and engineering project that aims to demonstrate the feasibility of fusion as a large-scale and carbon-free source of energy. Located in France, it involves collaboration among 35 nations including the EU, the US, Russia, Japan, China, South Korea, and India. ITER seeks to replicate the fusion processes of the Sun and is expected to produce 10 times more energy than it consumes. The project is a crucial step toward realizing practical fusion energy, pushing the boundaries of technology and international cooperation in energy research. 3. The Tokamak development 1950s present. The Tokamak is a device designed to confine plasma using magnetic fields in the shape of a torus, and it has become the most common type of fusion reactor design. The first Tokamak was developed in the Soviet Union in the 1950s, and since then various versions have been built worldwide, including the joint European Torus jet in the UK and the East in China known as the artificial sun. The Tokamak's design has been pivotal in advancing nuclear fusion research by allowing scientists to study plasma behavior under controlled conditions, making significant strides toward achieving sustainable fusion energy. The ongoing developments in Tokamak technology continue to shape the future of fusion energy research and its potential applications. China's recent achievement with its experimental advanced superconducting Tokamak East, commonly referred to as the artificial sun, marks a significant milestone in the pursuit of nuclear fusion energy. On January 20, 2025, East maintained a high-confinement plasma state for an unprecedented 1,066 seconds, surpassing its previous record of 403 seconds set in 2023. This development indicates substantial progress in fusion technology, which has the potential to revolutionize the global energy landscape. Future outlook and predictions. 1. Advancements in fusion technology. The successful operation of East for over 1,000 seconds demonstrates the feasibility of maintaining stable plasma conditions, a crucial aspect for future fusion reactors. As researchers refine their techniques and technologies, we can expect further improvements in plasma confinement and stability. This progress will likely lead to longer operational times, ultimately paving the way for commercial fusion reactors that can provide a consistent energy supply. 2. Global energy transition. Fusion energy represents a nearly limitless and clean power source. As countries grapple with climate change and the need for sustainable energy solutions, the advancements in fusion technology from projects like East will contribute significantly to the global energy transition. By the 2030s, there could be a shift towards incorporating fusion energy into national energy grids, reducing reliance on fossil fuels and mitigating greenhouse gas emissions. 3. International collaboration. China's contributions to the International Thermonuclear Experimental Reactor ITER project underline the importance of international collaboration in advancing fusion research. As East continues to yield valuable data, it will enhance the ITER project and similar initiatives worldwide. This collaborative environment may accelerate the development of practical fusion reactors, with a possibility of achieving operational fusion plants by the 2040s. 4. Economic implications. The commercialization of fusion energy could have profound economic impacts. The potential to harness vast amounts of energy with minimal environmental consequences may lead to a decrease in energy costs, creating a more stable energy market. Additionally, nations investing in fusion technology could see a boost in their economies through job creation in research, engineering, and manufacturing sectors. 5. Challenges ahead. Despite the promising developments, challenges remain. Achieving a self-sustaining fusion reaction known as ignition is still a significant hurdle. Researchers need to develop reactors capable of maintaining the necessary temperatures exceeding 100 million degrees Celsius and ensure long-term plasma stability. It is likely that breakthroughs in materials science, engineering, and plasma physics will be essential to overcome these barriers. 6. Potential applications beyond energy. The implications of successful fusion technology extend beyond energy generation. Fusion has the potential to revolutionize space exploration, providing efficient propulsion systems for interstellar travel. Additionally, the research and technologies developed for fusion reactors could lead to advancements in other fields such as medical applications and materials science. 7. Public perception and policy. As fusion technology progresses, public perception will play a crucial role in its development. Education and outreach efforts will be necessary to inform the public about the benefits and safety of fusion energy. Policymakers will need to create supportive regulatory frameworks to facilitate research and development, ensuring that fusion energy can be integrated into the existing energy infrastructure. 8. Timeline for practical implementation. While the recent achievements are promising, experts caution that practical fusion power may still be decades away. A realistic timeline for operational fusion power plants could extend into the 2050s or beyond, depending on the pace of technological advancements and international collaboration. In conclusion, the milestones achieved by China's East represent a significant step towards realizing the dream of clean, limitless fusion energy. While challenges remain, the future of fusion technology holds promise for transforming the global energy landscape, driving economic growth, and addressing climate change. Continued innovation, collaboration, and investment in fusion research will be crucial in making this vision a reality.